So, welcome. Now let me make sure that I actually am recording. Good, because I forgot to hit record on Wednesday. So all of that amazing lecture that we did is gone forever. But of course it is seared indelibly in your minds and hearts. What?
What happened to the lecture?
I lost it. I didn't record it. I had it all open and thought I was recording, and then I wasn't.
That's cool.
Yeah. Yeah, it's cool. So, well. In any case, so I noticed that in this room, this screen shows up in the background, but unfortunately, let's see if I can get. Whoa!
Oh my gosh,
It's Dr. Picconiception.
This is meta.
So meta. Anytime anybody says this is meta, I almost always say so meta afterwards because it's just the proper response. Okay, so we learned homogeneous response, state response, right? So we learned how to solve the state equations in the state space form if there's no input. Turns out sometimes we want some input, so we gotta learn how to do that. It's not that bad, it's just a little bit more work. So, let us embark upon this. By an argument similar to that in the homogeneous response notes. Remember, I'm putting homogeneous in quotes because it's really like the initial condition response, but it's kind of a misnomer. So by a similar argument to that, we can solve a state equation with non-zero inputs. So now we have the BU term. BU term was gone before because we said that U was 0, then there are no inputs. So if we use the matrix exponential e to the negative at, or e to the at, oh actually e to the negative at is the one we prefer in this case, as an integrating factor. Do you guys remember that from your differential equations class maybe? Integrating factors, woo! We can solve the system of ODEs as follows. Okay. So, we got to solve, I guess I should plug this in too. We got to solve our state equation, x dot equals ax plus bu, for x, right? But there's a derivative, so it's a differential equation we have to solve. Now, if we rearrange this, we can write that x dot minus ax equals bu, right? We just subtracted the ax term over. And then let's use our integrating factor. We'll multiply both sides of the equation by e to the negative at. And we have to multiply it by each term, so we'll do each term separately. Minus e to the minus at ax equals e to the minus at bu. Good. So, this takes a little bit of insight. This actually is, if we were to use the product rule in reverse, we can recognize this to be the time derivative of something. So I will say d dt of, and I want you guys to help me with what the term is. So what is this left-hand side? If I was to take the time derivative of what would I get that left-hand side? So so the product rule we need to use when we differentiate if we have two terms that both depend on time in this case. They both depend on time multiplied by each other, right? So you take the derivative of one, multiply it by the other, and you add it to the derivative of the other, multiplied by the first one.
So are you going to get e to the negative 2at for both derivatives of each term?
So it's actually, so it's e to the negative at times x. And
it's not x dot.
it's not x dot. It's because if we took the derivative of x first, we would get this. If we took the derivative of e to the negative at first, second, I guess, we would get negative e to the at times ax. So that is it's kind of like, it's a trick, right? I mean, like, I don't expect you guys to be like, oh yeah, I can totally see that. But it's good to see these tricks because one day we might find yourselves wanting to derive something like this. So it's good to learn. Okay, and that's still equal to e to the negative at bu. So now we're prepared to integrate, right? So I've said integrating. So integrating, we get the integral from 0 to t of, we'll use a dummy variable d ta, and then e to the minus a ta x, and then so we're integrating with respect to ta. Okay. On the other side, we have the integral from 0 to t of e to the negative at. Well, we can just use the same integrating our dummy variable ta in this one too. B u d ta. Okay, those are separate integrals. Okay, so this left-hand side, I mean, it kind of looks intimidating, but this left-hand side simplifies really nicely. So integral from 0 to t, this is a derivative with respect to ta, but the integrating factor, the variable over which we are integrating is ta. So we have actually a sort of, it's not a real algebraic cancellation, but there is a sort of cancellation that happens, but it's calculus, not an algebraic cancellation. And we're left with just the integral of d something. And what's nice is that integral is just whatever this term is. It's just like if you took the integral of dx with respect to x. That just gives you x plus a constant. Yeah, essentially. It's like you took the derivative and they took the integral, which is just like being like, yeah, we'll just stay here. Yeah, and the other side, we'll just leave that term. We'll just leave this as the integral from 0 to t of e to the negative a ta b u d ta. So we'll evaluate the left-hand side, which is conveniently just e to the negative a ta x, but then you have to evaluate it at t and then evaluate it and subtract the evaluation at 0. So let's plug that in this one step because we don't have infinite time. So e to the negative a, plug in the t, x, it's x of t, but we're going to suppress that, minus e to the negative a times 0, the time equals 0 on that limit, times x of 0, right? That's the initial condition.
So it's really just x of minus x of 0?
So yeah, so this ends up, this is actually the identity matrix. If you were not sure about the matrix exponential, then you could always go back to our definition of the matrix exponential and say, what happens, so this is e to the at, what happens if t is 0 in this series? It's just I, yeah. So if you were confused about what is the matrix exponential if the t is 0, it's just identity matrix. So I'll actually put a little, this is just the identity matrix. Good. And then the right-hand side stays the same. Of e to the negative a ta b u d ta. Now, I probably should have put like implies on every one of these lines. Like implies, and etc. But it was, understood that that's what it's doing. So now we're here. We're almost done, right? So we almost have x by itself. And that's what we're going for. We're trying to solve for x. So let's write it. So there are two ways of writing this result. So I'm going to write it two ways. So x of t. So I'm going to show the of t here. It didn't change. It's the same x that was here. X of t equals e to the at x of 0. And then there's going to be another term. So plus e to the at times the integral from 0 to t of e to the minus a ta b u d ta. Now, how did I get that? There were a couple steps that I did. Solving for x, so I added x naught, x of 0, to both sides, right? The initial condition to both sides. So that's how this term got here on the right-hand side. But then I had this e to the negative at on the left-hand side multiplying x. So I had to multiply both sides by e to the positive at, left multiply. Remember, in linear algebra, the order matters. So we have to left multiply by e to the minus at. We had to left multiply everything on this side by e to the at. Okay, now this can be simplified. There's one more step that we can simplify this, so I will do that. These are two forms that you'll see, so I wrote both forms. So the first term is the same, e to the at x of 0, plus, and then what we're going to do is we're going to bring this e to the at inside the integral, which isn't really necessary to do, but it's often done for a specific reason that I'll mention after I write it down. So that's a t. Integral from 0 to t of e to the a. Now you can combine these two exponentials. It's a, and it's going to be t minus ta. And then b u d ta. Okay, this is one of the reasons why we should use that dummy variable ta, because sometimes it matters. Yes?
Why is the negative going from the a?
On the right-hand side here?
No, farther down. The last piece where you went e to the a.
Because you're combining
The minus is there.
Oh,
It's just on the ta term. But we combined it with this, the t term is positive, and so we just stuck it in there. Yeah. So the reason why it's written like this, well, one of the reasons why it's written like this, is that this is a very special type of integral. It's called a convolution integral. Convolution integral. And unfortunately, I don't think we have time in this class to go over convolution. It's a really, really cool concept. I think it's the only concept that I find to be really key in system dynamics that I don't think we have time to cover. We cover a lot, but I don't think we're going to have time to cover it. essentially, this convolution integral comes up a lot when you're trying to solve for what the output is when you have different inputs. And it's really useful, and it's really cool, but yeah, we probably won't get there. But it is in the textbook. It is covered in the textbook, so please, if you've got time, go over the convolution stuff. It's pretty cool. Now, note, matrix and vector differentiation and integration are defined element-wise. So, for instance, we talked about this before, but I wanted to make sure that I drove it home. d dt of a vector, say x1 and x2, say they're both functions of time. So when I say this vector, what I really mean is this is a vector-valued function of time, right? Take the time derivative of a vector-valued function of time, you just take the time derivative of each element. So dx1 dt, dx2 dt. So just what you would hope is the definition. So that's that is that, and we have ourselves this, this solution. So the big takeaway of this lecture is that we have a solution now for the state equation, even if you have an input. Okay, you have to do this integral, which this inside here is, if you multiply this all out, it ends up being a vector. So you have to take an integral of each element of the vector. But, I mean, it's just an integral. And so if you have an input that has a nice form to it, and it's not super complicated, the function, then you can integrate it no problem analytically. You can always also numerically integrate. So you could have some arbitrary form of your input, and you could just numerically integrate it to get an approximate solution, which is very common. That's what simulations do. So, okay, I think I'm going to switch over now, and we're going to move on to the eigenvalues and eigenvectors set of notes. So.